Hey everybody, today I'm going to be solving lead code question 162, find a peak element. And yeah, I've never solved this question before, but I think I have an idea of how to solve this question. Let me just give like a background on what the question is actually asking and some of the constraints, because this one is funny because they want us to write an algorithm that runs in log of n time. Let's see. So let me just quickly read through the question. So a peak element is an element that is strictly greater than its neighbors. So for example, this is a peak element, 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 right? Pretend we had a list like just like this. Is this a peak element? No, it's not a peak element because it has to be strictly greater than its neighbors. But one constraint that you'll notice on this question is like no neighboring elements are gonna be equal. So basically saying nums I is definitely not equal to nums I plus one for all I. That means like they're all like it'll never be a case or never will be a case where anywhere in the array is flat. And that's key thing to notice here in this problem. What else? Given a zero index, find a peak element and return its indices. If or in its index, if the array contains multiple peaks, return any of the peaks. So I just need to return any of these peaks. I don't need to return the highest one, the lowest one, the one that's in the middle. I just need to return the high or just any, right? And then another constraint that you need to take into account is like the bounds of the array, the very left of the array, and also the end of array is always less than like the so basically the bounds are basically negative infinity. So this very last element is always greater than like its left, like because the end of the array there's nothing. So it's basically saying like the bounds of the array, think of them as like being negative infinity, like the left and right bounds. So you must write an algorithm in of log n time. And when I start thinking of log, like since it says log n time, I start to think we need to do some sort of binary search. If we did this using like I mean, this question would be kind of easy if we just had to do a linear search. If we can do this in like O of n time complexity. And how we do it in O of n time complexity is just like literally for each element in the array, compare it to its left like neighbor and its right neighbor and see if it's greater than its left and greater than its right. And we do that for every single element. So basically when we run into 3 here, we see it's greater than left and greater than right. And then we return index 2, which is a peak element. But we need to do this faster. We need to this is not acceptable. We need to do a log of n time complexity. So how I'm going to do that is through a binary search. So we just need to find a peak element, right? So how binary search usually is you compute the middle of your search space. When you first start, the search space is literally this whole thing right here. Is literally like this whole array. So we compute the middle, and the middle is here, right? First, we check, is this middle element the peak element, right? If it is, if we magically land on the peak element, we just return the index of that element. If we don't end up on that, like if it's not, if it's like one side is greater than it, we know it's not the peak element. So which side will we look at? We'll look at the side that's we'll basically search on the side that's it has a greater element than it. So basically what we have is like we'll compare element. So if it's not the peak element, right? If we pick an element and it's not the peak element, that means it has one side that's less than it and one side that's greater than it. Because if it was less, well, could it be less than both? Oh yeah, it could also there's multiple cases. It would be like, okay, when we look at an element, there's kind of 3 cases. Element. there's three cases. There's we're greater than both. If we're greater than both, just return you are peak, right? Less than both, like you're kind of like at the low, right? But then like you're greater than one side, and kind of less than other, greater than less than other, right? So either these are the two options. Like you're either here, you're the peak, or you're like in this middle right here. So what we're gonna do is like, since we're the element, like if we are the peak element, we just return. But if we are not the peak element, we're gonna pretty much only search on the other half that's greater than my element, because we know there'll be a peak over there, right? So we can pretty much cut out half of this search space because we know there will be a peak somewhere on the very right of us, right? Because since this is lower, I don't know if there will be a peak there. It could just keep getting lower and lower and lower till, right? But I know definitely there's gonna be a peak somewhere to my right. Like cancel this out, because if there wasn't, like it could be my next element beside me, but essentially because I know there's one greater than me, I like that one might actually still be the peak, so I want to keep that in my search space, right? Because a peak is something where it's greater than its neighbors. So I can pretty much delete the other ones because I don't know if there's a peak there, but I know there's a greater element than me to my right, so there might be a peak there, so I can search in that space, right? So I delete that. Now we look again in the middle here, right? And here again, pretend we this is actually less than both. So what we're gonna do is, since it's less than both, we'll just always take the right side. Yeah, since it's less than both, we're always gonna take the right side. It's kind of arbitrary. If it's less than both, we can choose either left or right. But now we're deleting this. Like we're actually losing a peak here, but we still know there's a peak on the other side because I know I'm great. Like elements to my right and left are both greater than me. Like pretend the array already stopped here. Like pretend there wasn't this area. Then this element beside me would actually be the peak. Like my neighbor would actually be the peak because like the bounds are negative infinity, right? So again, so like we cut off that search space. And then finally, let's say this is the middle. Or sorry, yeah. And then finally, let's get to the middle here. And now we're greater than both. Now we found a peak, and we can return that, right? Or let's do this, right? Because pretend like we calculate the middle. It's here. Yeah, we calculate the middle, and we get this other value, right? We say we always take the right side, so we'll literally always take the right side, and that's what we do here. And then now what happens? We say when we always take the greater side, right? So now we'll calculate the middle. We'll always take the greater side. So we'll start cutting the search space, always taking the bottom side because now we're on the hill until we finally get to the answer. And that's this right here, and this very side is actually a peak element because it's greater than negative affinity because we say the bounds is greater than negative affinity, and its left side is less than, like it's greater than the one on its left. So I think through a binary search we can solve this question. Hope that makes sense. That's kind of the intuition between it. You pretty much have three cases. You're always going to want to search on the greater. If you hit any of these two cases, you're always going to want to search on the side where you know for sure there's a greater element. And if both sides are a greater element, just arbitrarily take the left or right. You can even just freestyle that, but I'll make it so that it's always looking the right. And let's just go ahead and implement that. So how this usually works is, like, we're going to do a binary search and find a peak element. We know that there is a peak element, right? So what we're gonna do is we're usually with binary search we have a left and right pointer, and that just kind of like determines where our bounds are. Because so that just got really messy. Then we have right. We first keep we have to usually you keep track of your left and right bounds, and then like depending on like pretend I cut this search space in half. What I'll do is I'll move my left pointer like all the way up so it's no longer looking ever at that half. So this is like a modified binary search. So left pointer 0, length of nums -1, while left is less than right. Kind of like I'm just arbitrarily returning left right now, but actually let's not. Yeah, because we're doing it while left is less than right. If they equal the same, then we could just return any of them. So I'll just arbitrarily return left because at this point left is equal to right. So I could also return right if I wanted to. So like I said, we have to calculate the middle, and how you actually do that the most efficiently is you take the right minus left, and then you divide that by 2. That will get us the middle. So, and then you could like sometimes you in different binary searches you're gonna like if you have an array of like 3 elements or 4 elements, right? 1, 2, 3, right? This one clearly the middle is 2, right? But pretend in binary search you're gonna have to, if the array is even length, this is the middle or this is the middle, and depending on your algorithm you could choose like the lower middle or the higher middle, and in some binary search problems that actually matters. But in this problem we just take divided by 2 and we're kind of taking the lower middle. So if nums, so we'll look left equals if mid -1 is less than 0. What are these numbers? So the elements in here could be like anything. So let's say float -infinity, because like that's what I said. Like if it's out of bounds, if -1 is less than 0, then I'm looking at like that's going to be -infinity. Else nums, put mid there. So I'm looking at my left and right. Float mid +1 greater than equal to the length of nums, else mid -1. So I'm looking at my left and right. If nums mid is actually greater than left, and num, or let's just store it, mid val. This is kind of a tricky question. If the mid val is greater than left and the mid val is greater than right, we return like the index. If we do some if the mid val is less than the left and mid val is less than the right, we can do mid equals left plus, oh sorry, mid val. I have to say mid val here actually. I almost just overwritten my my pointers. If the mid val is less than both the left and right value, Like I said, I'll just take the left side, or sorry, left equals mid plus 1, else I'm going to want to take the greater side. So elif, if the right val is greater than me, I'm going to want to search there as well. So I'm going to bring my left there, else right equals mid minus 1. Oh shoot, mid, left, right, left, right. I'm in an infinite loop. Right minus left divided by 2. I put myself in infinite loop. Let's debug. So you start with left and right. All right, let's just like right here. Quickly debug. I actually debug this properly. So we start with left and right. Let me name it here. Maybe my algorithm doesn't even work. I'm pretty sure it works though. The index here is 0, 1, 2, 3. So we start 3. 3 minus 0. 3 minus 0 mid. So 3 minus 0 divided by 2 is 1. If you do the double back. So the mid pointer is here. Right? If the mid minus 1 is less than 0, else, then do that. Else, yeah. So I take nums mid minus 1. So I take this one. Yeah, I'm comparing that. That's my left value. My right value is mid plus 1 if it's greater than equal. Okay, yeah. Else nums mid plus 1. Okay, so I'm taking the right values. I'm comparing it. If the mid value is greater, so the first one should. So the first one should hit. It should hit. So the right val is greater than the mid val. It should go here and it should move left equals mid plus 1. It should have moved it up here, right? And then I'm taking if. It should have moved it there. Let's see. Let's see how it ran on the first one. Print here. Well, it's breaking. It's passing on this one, but it's just not. It's not passing properly on this case. Let me look over it. If the mid plus 1, if the right value, it might be because we're taking the middle element each time. That work? Okay. Sorry, I just threw that in there for no reason. What's the mid value I'm calculating here? If the right value is greater than the mid value, if the right value is greater than my mid value, I'll just move my left. Okay. Ooh. Okay, I'm dealing with some I'm dealing with some bounds issues right now. Trying to think. So here, sure, 1, 2. I get 2. That's clearly not the middle. Oh yeah, something's wrong, right? Okay. Let's go on this test case. Right. This test case is actually like this is how I'm gonna break out my infinite loop. Like I'm getting stuck on one specific index. I just need to know. Now I'll print like print left or right at this point. What? Okay, I'm breaking on this. It's not working on this case, which is more simple, which is great. Left and so. Okay, what's happening here? I start in left and right. 3 divided by 2 quotient division. It gives us the first index here. Then I literally move here. If the mid val. Let's see why it's breaking. 1. So the mid val is kind of like moving. Okay, who sets mid? Return mid. If the mid val is less than the left val and mid val is less than the right val, we move the left. And if the right val is greater than equal to the mid val, so we move. Oh, okay. We're moving the right way too far. Oh, wow. Okay. See, this is what happens when you have binary search. Like, you really have to deal with the bounds. So I'm getting stuck where the mid value is just like literally fluctuating between 1 and 0. How did that happen? 1. Oh my god, because I just have to do here mid plus. Oh yeah, because you have to do it based on the middle here. Is it left? Okay, I guess I don't know how to implement binary search correctly. Got it right, got it right. I just didn't know. I was calculating the middle. I was calculating the index, but like you have to add, like you have to calculate the middle. It gives you the difference. It gives you the difference. It basically gives you like the length of the array, like the middle of the array, but you have to add it to the left pointer. So if the left pointer is here, and then we figure out like the side, like this, basically because here we're calculating how big is half the array. So we have to add half the array to the left pointer, and that will give us the middle of wherever we're looking at. Ooh, that was a really good question. Hopefully you saw kind of how I debugged it. I kind of stared at it until I figured it out. But yeah, give me tips on how I can improve on that, honestly. What's your strategy to like getting unstuck from a question? Because in an interview, like the interviewer would be like, this guy is not progressing and probably would have failed me. So, all right, see you on the next video.